What we need to do now is to state Faraday's law and Lenz's law. We know that the EMF is proportional to BA, in other words, phi, which is the change of flux, the rate of change of flux with time. Okay? For example, this magnet is not moving, there's no change of flux, so there is no current induced, or no EMF induced in the wire. Here, the magnet is moving into the coil. As it moves into the coil, the amount of flux linkage increases with time because the magnetic field becomes stronger as it gets closer to the coil. So it depends on the rate of flux linkage divided by time. However, each loop will also link the same amount of flux, so it also depends on the number of turns of the wire. So EMF is equal to N d phi by dt. So it's N times by the change of flux linkage divided by time. When you move the magnet away, the amount of flux linkage reduces. You could say that the magnetic field collapses. This change of magnetic field, which is linked by the coil, and for every link there's a certain amount of flux change, so it depends on the number of turns, then you will get an EMF there as well. Faraday's law says just this: the EMF is proportional to the rate of change of flux linkage. In a past mark scheme in May 2007, they ask you to define Faraday's law. The induced EMF is equal or proportional to the rate of change or the cutting of the magnetic flux. That's all they need to do. So it's proportional to the rate of change or the cutting of the magnetic flux. Okay, this equation has got a negative sign here. Now this is an important aspect because this brings us on to Lenz's law. The direction of EMF is such to tend to oppose the change producing it, which means that when there's a change of flux in the coil, there will be an EMF induced in the coil that will try to oppose the change that's producing it. Okay, this demonstrates Lenz's law in a very interesting way. Now, we know that as the magnet moves into this coil, we have this metal bar here, then there will be an EMF induced in the bar. We'll move it in, and you see that a current is flowing in this direction. However, we know that if we get a current, then what's going to happen is that this current will itself produce a magnetic field. Okay, so moving this in induces a current in the coil, in this hoop, and the current itself will induce another magnetic field. Now Lenz's law says that the direction of this magnetic field will always be in the opposite direction to the change that's producing the current in the first place. In other words, if the north is moving in, the current will flow in such a direction that it will try to make this a north as well, this side north, which will try to oppose the arrival of this north. So if you watch carefully, as it moves in, the magnetic field lines travel this way, anti-clockwise there, clockwise there, which means they're trying to make this into a north of this coil here that will reject that north. Now if I try to move this out, the current is going to be induced in the other direction, and it tries to make this side south because it does not want the north to leave. Okay, so whatever is happening here, the current induced will always produce a magnetic field which is trying to oppose it. This is Lenz's law, and it is a fundamental fact that this must happen. An example would be the conservation of energy. If this magnet were to be moving in and the current were induced in such a way that this became a south part, the south end of this solenoid, it would attract it even more. That would make more current, would attract it even more. So by slowly introducing the magnet, the magnet by itself would move faster and faster and faster because it would be pulled by the magnetic field which was created by the induced current. This can't possibly happen. It's a violation of the conservation of energy. You can't create energy. And likewise, if you move it away, and this is the north moving away, this has to be south to oppose it. If it was north to encourage it to be moving away, then it would get faster and faster and faster. This is also a violation of the conservation of energy. Here we have a person that is rotating a magnet inside the coil, or she's pushing the magnet into the coil. So she's trying to work this to produce a current, which is going to measure here. Now, the more she moves it, the more current she's going to produce in the coil. However, the current that is produced here will itself produce a magnetic field which will try to oppose the change that's producing it. So she will always find some extra resistance. She must do this, otherwise the conservation of energy has been violated. It becomes more difficult to push the magnet into a coil with more loops because of the magnetic field of each loop resists the motion of the magnet, and this is Lenz's law. The direction of the induced current will always try to oppose the change that is producing it.